Now let's talk about a simple web crawler. How can we design such system? So as usual, let's try to go through requirements one point at a time. And first, before even going through our requirements, web crawler, just a simple definition of that is, which really helps us to automatically traverse the web by downloading web pages and following the links from one page to another. So in real scenario, it's ideally used to index the web for search engines, or collect data for research, or to train models, LLM models, and monitor websites for changes and all that stuff. So that's the practical application of this web crawler system. So now let's discuss about requirements that we should meet while we are designing the system. The first requirement is we should be able to crawl the web starting from a given set of seed URLs. So seed URLs can be something like, URL of popular search engine, or popular news sites, or tech blogs, or social media platform link, just to get started with, depending upon the traffic that it is hitting the specific sites. We can just prepare a seed URLs and then start from that. So that is something we can crawl the web starting from those given set of seed URLs. And the second requirement is we should be able to extract text from that each page, the site, the URL that we are visiting, and store that text for later processing. It can be for anything, like I mentioned, for training the model, or indexing the content of the web page and all that stuff. So these are like minimal criteria that we should design the system to meet. And others good to have is actual processing of text data once we store it in a database, like can be training a model or anything. And then good to have if our system can handle non-text data, can something like images, something like images, videos, or the content in the tables and all advanced stuff. If it is handling, then that's better. And handling dynamic content, maybe JavaScript rendered pages, like frameworks, React, or Angular, or Next.js, whatever they're using. How can we handle that dynamic rendered pages using maybe headless browser like Puppeteer and all that stuff? And also we should maybe good to have if our system can handle login required pages. So there will be some websites that needs exclusive credentials to access the content of their websites, and accordingly we can just crawl that and store the content of that page. So these 4 points are good to have, but we might not discuss in this, but these 2 points we'll try to discuss how can we achieve that. And coming down to non-functional, first the point that we should meet is we should keep our system as fault tolerance, and should be able to resume crawling without losing the progress of whatever the step that it failed at. Okay, so that's first point. And the second point is there will be a website with all websites will be with the robots.txt file, and we should respect that whatever the rules are configured. And also we should not really overload website servers, frequently hitting them to crawl the content of that. So that is something we should respect. And coming down to scale, we should handle 10 billion pages, like a peak traffic. We should be able to support that handling of 10 billion pages. And our system, now the thing that we are trying to design, should be able to crawl this 10 pages, the scale that I'm talking, in 5 days. So how are we going to design a system such that it's going to help us retrieve 10 billion pages in content of the 10 billion pages in 5 days? And the other good to have is like security to protect from our malicious actors the services that we are designing. And if we can optimize such that cost of the instances and computation that we need can be adjusted within budget constraints, and adhering to compliances based on regional locations. If you are in EU region, there will be specific regulations that we should meet, and depending upon regulations, if we can consider, that's good to have. But again, this I'm just mentioning, and we will not be discussing in detail. So now that our functional and non-functional requirements are clear, let's since this is not a public user facing application, more of an systems infra, the services that we are trying to design, so we'll have a system interface. So let's first make ourselves very clear what is going to be the input and output of the application. So input is like I mentioned, it is going to be seed URLs to start crawling from, and the output is we should be able to extract the text present in those URLs and store it in our systems. So that is a simple system interface, input and output. And now let's just briefly understand the data flow of our application. So the data flow is first step is going to be take seed URL from maybe it can be frontier queue or whatever, we'll discuss more about that. And then once we have that URL, we need to request an IP address from that DNS. And once we get the IP, we will try to fetch the HTML content from that external server using that IP. And after that we have HTML, and we'll try to extract text data from that HTML and store the text whatever we extracted in the previous step in our database, whatever the persistence layer that we're trying to add in this design. After that once we store, we need to identify if there is any linked URLs from the text data that we tried extracting from HTML, and if so, I need to add them back to the list of the URLs to crawl. Basically I should again append it to my queue, frontier queue, so that gets picked up. Yeah, so this thing is something that needs to be repeated until the URLs are empty or there are no more URLs to crawl from. Okay, so this is the rough data flow of our system, the take seed URL and these rough 5 to 6 steps. So I think this the data flow should be very clear of these steps that we just discussed. So since now we are clear exactly how the flow of our system is going to look like, let's try to discuss one point at a time from functional requirements as a high level discussion, and then take it from there. High level discussion. So like we just saw the flow in the above data flow, that is something I try to represent in the components here. Here the core components, like you see, we have the frontier queue and the crawler, the DNS, web page, and S3 text data. So if I talk about one at a time, frontier queue is basically this is where we'll try to put the queue of all URLs that we need to crawl. Maybe we'll start, like I said, with a set of seed URLs and add new URLs as we crawl the web. Here it can be any queue, it can be Kafka, Redis, or SQS, or whatever that we are comfortable with. And crawler, if you see, the main responsibility here we're trying to give it to it is fetch the web page, extract text, and extract URLs. And if there is any URLs, we'll just put extracted URLs back on the queue. And in this crawler, we'll try to receive domain receive IP addresses using the domain names by hitting this DNS, and that it's going to help us for DNS lookups and get that IP address. And using that IP address, it crawls this web page content, and then executes this task, extracting text and extracting URLs. And accordingly, it will store that whatever the text that was extracted in our S3 text section. And this is like the rough components, at least to begin with, the decent flow of achieving the requirements that we have drafted above. Yeah, so this whatever the things that are in our these are like in our control, and these are something like external that we are trying to rely on, DNS lookups, DNS providers, and web page that we are trying to crawl from. Okay, so let's go one point at a time, a deep discussion. The first thing is fault tolerance and resume crawling without losing progress. So here right now, if you see in the above picture, crawler is doing a lot of things. It is trying to fetch web page. First doing DNS lookup, and then fetch web page, extract text, and extract URLs, and still if we had a logic of respecting robots.txt and all other stuff, it is trying to do a lot of things. So whenever we try to observe such things, the immediate thing that should come to our mind is we need to somehow break it down into smaller steps, so that we'll have a good point of checkpoint where exactly that we need to resume from. So after having observe that we can split this one into two things. One is it can just do URL fetcher, and another is the URL and text extraction. So if we try to split it, this is how it's going to look like. So now the design is something in this way. We have separated into two things, the fetch and store web page. So this what this does ideally, whatever the raw HTML that we have, it will try to store in the S3 bucket, and once we have that S3 URL, it will put that S3 URL in our parsing queue. So that URLs whatever we are appending into our queue will be picked up by our parsing worker. So here this is where actual text extraction and URLs extractions will happen, and accordingly here once we pass in these S3 links, it will try to download the content of this S3 from this S3 bucket. So that is this first step, downloading HTML from that S3 link. After downloading, we do some processing of the logic, whatever we have to extract text and all. Once we have extracted text, again I'll save the S3 link for parsed text back to first to bucket, and then update our URL metadata for keeping track of even the text S3 link URL. And if we found any the link to another URL, I'll put back this onto our frontier queue. So now that this, if you see, it just does the job of looking DNS lookups and fetching that web page, and just saving the raw HTML, and parsing and all is something delegated to this workers, and this queue will make sure that these are decoupled and will be able to scale it independently. So this is something we can make this work to delegate or split the tasks and all. And even if something fails, this queue is something is going to help us handle that. Let's discuss like what if, like, first in the failure scenario that can be when we are trying to look up the content of the specific URL of a website, that might fail. So what happens if we fail to fetch a URL? So it can be mainly due to that website can be no longer there on the internet, or it might have moved, it might be down, or it might be slow or experiencing some downtime and all. So to confirm, we'll want to retry, of course, on failures, right? So how can we do that retrying on failures? So here are the couple of approaches that we can think of. What if we fail to fetch URL? One straightforward approaches can be in memory timer, so that I'll try to wait for a few seconds and then again try to retry to hitting the same URL and see if I can still be able to access that URL and get the content of it. Ideally this approach is something not going to work in just few more seconds. Again, it really succeed. And also, what if the crawler itself goes down? That's again the problem in this approach in memory timer. So that is something that we cannot stick to it, or we cannot consider in this scenario. And another thing is Kafka with the manual exponential backoff. So now we'll try to maintain for whatever we are failing here, we will try to maintain separate topic just for failed URLs, and a separate service that reads from this maybe can be a failed topic or whatever the name that we can keep. And this way we could store the URLs in that queue, and it gets picked up by crawler. Again we'll try to hit it again, the kind of retry. So we could store how can we do this is basically we could store the time that the next fetch should occur in the message itself. The one which I'm trying to put on the queue. So when consumer, meaning our caller, tries to read some message, it really waits until that time to retry. So this way we can make sure that we are retrying after a specific time, not immediately. And then a good way to think of to achieve this retry logic. And this is something, the downside is we should implement all this logic manually, whatever the retrying that we just talked about of storing the time with the message itself, and then waiting till that time is reached, and then try to process it and all. So the straightforward approach is basically using SQS queue. I'm a AWS simple queue service with exponential backoff. So by default, it comes up with all of this retry logic and everything. So we'll have a configurable exponential backoff strategy out of the box. For example, there is a concept of visibility timeout in SQS. Let's say if one worker has picked up for that 15 seconds, that will not be visible in the queue, so that others crawlers or workers cannot pick it up. And after that, it will try again for 2 minutes or 5 minutes and up to 15 minutes, and meaning it will put back after 15 seconds back in the queue, and some other crawler will try to pick it up and all that stuff. Even after it failed after 15 minutes, it will push it to dead letter queue. So again, this is good strategy to try up to like in n times, maybe 3 to 4 times, and then put it to DLQ. We don't want to retry infinitely, right? So I think this out of the box strategy is something that really helps us to achieve in the scenario. What if we try to fail fetching the URL? So that's how we can try to address conditions. And the next question can be like, what if the crawler itself goes down? The crawler, whatever that it was trying to handle DNS lookups and fetching the web page and then extracting raw HTML. This straight the thought that really strikes us, how we can just spin up a new one and URL will still be in the queue. So basically here, why URL will stay in the queue is basically until our crawler worker confirms it will not be erased from the queue, whatever that we are using, since it is failed and we have not acknowledged it. So it will still be there in the queue, and it gets picked up by the new instances that we'll be trying to spin up. So here we can use either Kafka or SQS depending upon our comfort of the choice. So here if we say the Kafka scenario, it retains messages in a log and does not really remove unless a consumer or the worker really confirms that it was successful. If not, the new crawler or the worker will pick it up the latest offset thing, and then it will be retry that as usual. And in SQS, like we just discussed, visibility timeout is the concept that will really help us to help other workers to pick it up. So this is how it's going to look like after considering the above points heading. So here now frontier queue we are considering the SQS because we don't want to add our own manual retry logic and other stuff, and just want to use out of the box features that we get. And then there is a dead letter queue after retrying on failure with exponential backoff. Even after the 2 minutes 5 minutes, the window that I was just specifying, we'll just put it into our dead letter queue. Maybe later some developer or we can just inspect what might be the reason, or maybe we need to have periodic purging logic which can remove from the DLQ so that storage will not be piled up. So yeah, this is a simple way of handling the problem that we just discussed above. And the second point that we need to address is respect robots.txt and not overload website servers. So just let's try to understand what is robots.txt. So basically that's a file where that websites really use to communicate with web crawlers. So it really helps or tells crawlers which pages they are allowed to crawl from that website and which they are not. And also it tells crawlers how frequently they can crawl this site. It might look something like this user agent. So basically it allows all agents, and disallow they are specifying that whatever the pages are present under /private, it's something that you are not allowed to crawl from. And crawl delay is like 10 seconds that should wait between the consecutive requests that it's trying to make to that website. So yeah, what we need to do here, the flow ultimately is something, it should be in this way. Fetch the robots.txt file for that specific domain, the web page that we are trying to hit, and will try to parse that robots.txt file, so and store in our metadata DB. So here we are trying to create a new table called domain. So for that domain and lastCrawlTime and along with that robots.txt file that we have extracted, we'll try to store in this metadata database. So once we store that, and when something's when we try to pull URL off the queue, we'll first check the rules stored in that domains table for that domain. So if the URL is in disallowed list, so we will just acknowledge the message and move on to the next URL from the queue and all. If URL is allowed, we will check the crawl delay directive and see if it is something that we are meeting. Then if it's not passed, we'll put it back on the queue using the delay seconds concepts in SQS, so that it will be trying out after that specific time thing. If passed, we'll try to crawl the page and update the last crawl time for that specific domain. So this is how the simple flow it's going to be like, respecting the lookups of by the crawler in the metadata database using the domain and all, and the rest it's going to be the same. And the rate limiting, so is like we'll really want to limit like one request per second for that specific website. So how are we going to do is, we'll try to add a simple maybe let's say here Redis to just help us store the count maybe per domain. So we'll try to use Redis sliding window algo to just check request counts per domain per second, and accordingly see if it is not reached the limit, and if it's not, we'll try to just hit it, or else we'll restrict for the time being. So, and the issues here, it might be of if several crawlers, meaning our workers, are waiting to make requests and simultaneously retry when the rate limit window resets. Okay, so they all try and one will succeed and the process will repeat. It's something like everyone is trying to do it at the same time. So how can we address that? There is a simple thing to address that synchronized behavior called jitter. So jitter is nothing but we'll just try to introduce a random delay to each crawler's request, so that we'll make sure that they will not try to crawl the web at the same time. So that is something we can handle using this rate limit. Fine. So this way, maybe I might not have explained detailedly, but high level idea is the intuition is what I'm trying to give for this rate limiter and all, and to make sure that we try to do respect the industry limit of one request per second for a particular website and all. Okay, fine. So that's the thing. And the next point is, how can we scale to handle 10 billion pages and efficient to crawl 10 billion pages in 5 days? So this is very important discussion in this system now. So let's try to just discuss practical numbers. So assume average size of the page is 2 MB. Okay, so 2 MB. So typically AWS clouds, let's say most optimized network instance can handle about 400 gigabits per second. So converting it to bytes by 8 is something like 50 gigabytes per second. That's the throughput that we can send per second. So here we have 2 MB pages. So for this 50 GB per second, how many pages can we send is something 50,000 megabytes per second by 2 MB is something 25,000 pages per second is what one instance can process. And here we need to handle 10 billion pages, and this is like ultimate capacity of specific instance. We will never consider 100% capacity of a specific instance. So assume there might be network delays, response times and all that stuff. So we hardly consider 30 to 40% of that specific utilization of that instance. So considering here 30% of that, so 30% of this is so 25,000 is 7,500 pages per second. So now we know one instance can handle 7,500 pages per second. So 1 second 7,500 pages. So for handling 10 billion pages, how much time? So how much time is something roughly around 15.4 days. So if we use one instance and to process 10 billion pages, it takes 15.4 days for one mission. So but the requirement is we should achieve it in 5 days. So to achieve it in 5 days, how many missions is something that we need? 15.4 by 4, maybe I'm considering here 4 missions. So it gives us like roughly so we might need 4 missions, and if we have 4 missions we can achieve this 3.85 days. So we need 4 missions to reach a target of less than 5 days. Fine. So that's the number of missions that we need. And the common question here that's going to come is how are we going to scale parser workers, like which is actually doing the job of extracting the text and identifying URLs, and that it's putting back in the queue. So here we can straight away leverage auto scaling containers like ECS based upon the pages that are further left in the processing queue, and you just auto scale using that ECS task. I think this way we can just scale our parser workers, and since we need to handle this much of a scale, the DNS also, I think it's important for every request with domain. We not always try to look for that in our DNS provider, because that will also have an hard cap limit of hitting request per time based. So instead of trying to hit every time, maybe we might cache that lookups in our Redis, and also not just relying on one single provider. We can try to use multiple DNS providers so that we can smartly avoid this rate limit cap that we'll have on specific DNS provider, and use round robin of hitting that specific provider, and get the lookup IP address accordingly and all. So that way, in the scaling, when we are trying to handle this much of a traffic, is something that we can think when it comes to DNS and all. So efficiency wise, first thing, we should make sure that we don't really crawl pages that have been crawled already. So how can we do this one? Maybe simple metadata lookup. Before trying to crawl, we'll just have a look in our metadata, see if we have crawled that before. If yes, we will not crawl it again. If no, we will proceed with the whatever the logic that we have. But the magic of the internet is this: what if different URLs point to the same page? For example, example.com, www.example.com, so it might point to the same page. And also it's really possible different domains to have the exactly same content. So here we cannot now just compare URLs to see if that has been crawled. So now we need to compare it even at the content level. So if that has been already passed, and there is a content or something of that stuff in our DB and all. So here, how can we do now? Make sure we do compare the content also. The simple and straightforward approach, ideally, which is mostly preferred, is this: we'll try to hash the content of the that specific web page and all, and store it in our metadata DB with index. So that now when we try to get pass new thing, I mean pass it to parsing workers, we try to again hash that and see if there is a lookup match, and accordingly to proceed or not. Is that's something I'll just add a global secondary index in our metadata DB and add index column for that table. Other approach is something we can rely is using Bloom filter. So Bloom filter is basically, that's a simple probabilistic data structure that really allows us to test whether an element is part of a particular set. So then it's something we can straight away use the Bloom filter data structure in Redis, and try to maintain this in the Redis, and check if it is member part of that set which we already have in our Redis and all accordingly. Ideally, this is an overkill, and mostly the preferred approach is this hash and storing metadata DB with index. And also one more thing really that we should be very cautious is, what if the website has a link to itself? So it's something that really there's a chance that it might put us an infinite loop. So it is something that needs to be addressed also. So to avoid situations of this kind, we can add a concept called maybe depth field or something like that in our metadata DB. So if let's say I configure depth as like 3 or 4, so after meeting this number, we will not try that URL anymore, and then take on the next URL. So something that is how we can avoid this trap. So after discussing above points, so this is how it can be about the DNS cache we will try to add to achieve this efficiency whatever we just discussed, and the additional fields here for comparing the content, we'll try to maintain a hash and also the depth to avoid the scroll trap, so that now I can just have a lookup on the hash to just see if the content is already present in our sources. Fine, so that's the simple way of trying to meet this scaling to 10B pages and achieving in 5 days and all whatever we just discussed. So this is a simple design, and not maybe might not be that intuitive, but it really gives us a good insight, to at least to think in the direction of. And other things that we might really consider is, like I said, handling dynamic content, and to to handle the React or Angular pages and all, we can do this using headless browser like Puppeteer to render the page and extract the content. And we might need to monitor health of our systems or of all our services. We can use something like Datadog or New Relic to monitor the performance of crawlers or parser workers and everything, and alert us if anything goes wrong. And there might be scenarios where web pages will have large files, and maybe that's a good sign to look for content type content length header to determine if the size of the file before downloading. If it's too large, we'll just skip and not proceed with that web page. And and one more important point here, now we're considering it's just a one-time crawl, but what if you want to enable continual updates to our data source? Maybe we might plan to retrain the model every month, or our crawler is something we wanted to do, maybe index the search engine that needs to be updated regularly. So how can we at least think of is the rough idea. We can have a new component here somewhere, whatever we can name it as something called URL scheduler, that is responsible for scheduling URLs to be crawled. Okay, so rather than putting the URLs directly on our parser workers that we are trying to do now, we will try to put that URLs in our metadata DB first. And once we put in our metadata DB, the URL scheduler, the new component whatever we are trying to add, is something will be responsible for scheduling URLs by picking it from our metadata database by using some logic base based on last scroll time, popularity, or something on those lines. So that's how at least we can think of or discuss on. So to sum it up, this is a simple web crawler, and we did try to think in the direction of at least addressing one or two important points in either functional or non-functional sections.